Magnets may seem like ordinary objects, yet they possess extremely powerful forces capable of crushing objects in an instant. To transform raw rocks containing radioactive impurities into magnets with seemingly magical pulling power, the material must undergo an intense physical, mechanical, and chemical journey. From open-pit blasting sites and tanks filled with corrosive acids, to high-temperature sintering furnaces and powerful pulse magnetizing stations. Today, join Factron Process as we go behind the scenes of massive factories where magnets become a force that changes the world. The rare earth magnet industry is currently worth more than $20 billion and continues to grow rapidly, driven by electric vehicles, wind turbines, robots, and electronic devices. Demand for neodymium, praseodymium, dysprosium, and terbium has doubled since 2015 and is projected to rise by more than 30% by 2030. However, the global supply chain is heavily concentrated in China. The country accounts for approximately 60% of the rare earth mining output used for magnets, more than 90% of refining capacity, and as much as 94% of the world's sintered permanent magnet production. This dependence has turned rare earth magnets into a major geopolitical bottleneck. Export licensing measures covering certain elements and magnetic materials could slow supplies to the automotive, aerospace, energy, and defense industries. What would happen if this strategic material flow were restricted while alternative supply chains remained incomplete? The journey to create supermagnets begins at Bayan Obo in Inner Mongolia, China. A massive rare earth mine often estimated to hold more than half of the world's known reserves. Here, engineers conduct exploratory drilling, analyze core samples, and map ore bodies to identify carbonate rock zones rich in bastnäsite and monazite. High-pressure drilling rigs then create hundreds of holes more than 20 meters deep with drilling speeds that can reach approximately 5 feet per minute, before the holes are loaded with Ndfeb explosives. The blasts are triggered only a few milliseconds apart to break the rock while controlling the size of the fragmented ore. Hydraulic excavators then load the material into Cat or Komatsu haul trucks with capacities of hundreds of tons, continuously transporting it to the primary crushing station. While Mountain Pass in California is an important large-scale rare earth mine in the United States, China also possesses hundreds of ion adsorption clay deposits in the south. There, rare earths are commonly recovered using leaching solutions instead of drilling and blasting, as at Bayan Obo, allowing the country to build a more diverse supply network. But behind this strategic material lies an enormous volume of waste. Some estimates suggest that producing 1 ton of rare earth products can generate up to approximately 2,000 tons of waste rock, flotation tailings, and wastewater, depending on the ore type and calculation method. Near Baotou, an industrial waste reservoir more than 11 kilometers long has accumulated sludge from refining plants for decades. This mixture may contain acids, heavy metals, thorium, or uranium, raising concerns about soil contamination, toxic dust, and possible leakage into groundwater. Leaving the mining site, the raw ore is dumped into the feed hopper of a primary crusher. Here, manganese steel crushing jaws operating at hundreds of kilowatts compress and break large rocks down to approximately 100 to 200 millimeters. This process releases large quantities of airborne silica dust. If dust extraction systems and protective equipment fail to operate effectively, fine particles can penetrate deep into the lungs, causing tissue damage and chronic silicosis among workers. Ore that reaches the required size is mixed with water and fed into a horizontal ball mill, approximately 4 meters in diameter. Inside the rotating drum, Thousands of steel balls are continuously lifted, dropped, and driven into the ore, grinding the material to below 200 micrometers. A hydrocyclone system then classifies the mixture by particle size and mass. Coarse particles that fail to meet the standard are returned to the mill, while the uniform fine fraction continues to the flotation stage. The ground ore slurry is pumped into a series of industrial flotation tanks, where agitators operate continuously to keep the mineral particles evenly dispersed in water. Oleic acid or amines are added to selectively modify the surfaces of bastnasite and monazite minerals, making them hydrophobic. At the same time, compressors inject air from the bottom of the tanks, creating millions of small bubbles throughout the mixture. Rare earth mineral particles attach to the surfaces of these bubbles and gradually rise, while most of the gangue and non-reactive impurities continue sinking to the bottom. The froth rich in rare earth minerals is continuously skimmed into a collection trough, producing a higher grade concentrate before it moves to chemical refining and separation. Leaving the flotation trough, the concentrate is oxidizing roasted at approximately 1000 degrees to break down the mineral structure, then leached with hydrochloric acid or another suitable chemical system. The resulting solution is neutralized, filtered, and treated to remove iron, calcium, fluorine, and impurities containing thorium or uranium before entering the separation area. Because rare earth ions have similar sizes and chemical properties, the solution is pumped through a countercurrent solvent extraction system consisting of hundreds of mixer-settler stages. At each stage, the organic and aqueous phases are mixed and then separated, gradually isolating neodymium and praseodymium from the remaining elements. The NdPr stream is then precipitated as oxalate and calcined into an oxide powder with a purity above 99.5%. The oxide powder is fed into a molten salt electrolysis system operating at approximately 1050 degrees Celsius. A direct current of up to 30,000 amperes reduces the rare earth ions into liquid NdPr metal at the cathode, while the graphite anode produces gases containing carbon oxides. The molten metal sinks to the bottom of the cell, is extracted, and then transferred to a rotary casting device where it solidifies into NdPr plates or ingots for the alloy melting stage. NdPr ingots are blended with iron and boron, with rare earths accounting for 28 to 32%, boron nearly 1%, and the remainder mainly iron. The mixture is melted in an argon-protected vacuum induction furnace at 2500 to 2700 degrees for approximately 2 to 4 hours. The molten alloy is then poured onto a high-speed rotating copper wheel. Internal water cooling removes approximately 1000 degrees Celsius of heat in 1,000th of a second, forming flakes less than 200 micrometers thick. This limits free iron formation and distributes neodymium-rich phases more evenly before hydrogen decrepitation. The cast alloy flakes are loaded into a sealed chamber filled with hydrogen gas. Here, hydrogen penetrates deep into the internal structure, causing the alloy to expand, crack apart, and break into coarse powder particles resembling crushed stone. The material is then transferred into a jet mill to reduce the coarse particles into ultrafine powder. Inert gas is blown through Laval nozzles at a supersonic speed of Mach 2, twice the speed of sound. The particles collide directly with one another and fracture into an ultrafine size range of 3 to 5 micrometers. At this stage, the fine powder is extremely reactive and can spontaneously ignite in air, so the entire system must remain flooded with inert gas and completely free of oxygen to prevent a dust explosion disaster. The ultrafine Ndfeb powder is loaded into a non-magnetic mold under controlled oxygen conditions. A magnetic field of 1.5 to 3.0 Tesla aligns the easy magnetization axes of the Nd2Fe4b particles before a hydraulic punch applies several tens of megapascals. The compact is then cold isostatically pressed at 200 to 300 GPa to improve density uniformity. The blocks are placed on molybdenum trays and vacuum sintered at 2200 to 2400 degrees Fahrenheit. Over 4 to 5 hours, the neodymium-rich phase helps bond the particles, causing shrinkage and bringing the compact close to 100% theoretical density. Finally, it is cooled under controlled conditions and tempered at approximately 950 degrees Fahrenheit to improve coercivity and stabilize the microstructure. After sintering, the compact is extremely hard but brittle, so it is sliced into thin plates using high-speed diamond wire. The plates are then cut, drilled, or ground into discs, rings, rectangular blocks, or curved motor segments, with tolerances below 0.01 millimeters. Coolant is sprayed continuously to control heat and reduce the risk of Ndfeb dust ignition. For complex parts, material losses can reach 30 to 50% of the compact's mass and are sent to a rare earth recovery line. The finished pieces are then ultrasonically cleaned, rinsed with deionized water, and coated with Ni-CQ-Ni, zinc, or epoxy to a thickness of about 20 micrometers for corrosion protection. After coating, the components remain unmagnetized and are placed inside a copper coil fixture. A capacitor bank releases a high-voltage pulse of several kilovolts, producing a peak current of up to 50,000 amperes in a few thousandths of a second. The pulse generates a field exceeding 3 Tesla, aligning the magnetic domains and bringing the material close to magnetic saturation. Each magnet is then checked using Gauss sensors, Hall probes, and flux measuring equipment. Machine vision detects cracks, chipped edges, and coating defects. Representative samples are also subjected to heating and salt spray tests, while rejected products are demagnetized and transferred to the recovery line. After passing all inspections, the magnets are transferred to a safe packaging area. Because of their extremely powerful attraction, each component must be separated by plastic spacers or non-magnetic materials to prevent the magnets from sticking together, colliding, and damaging their protective coatings. The magnet assemblies are then secured inside shock-resistant trays. For products with particularly strong magnetic fields, the factory also places steel plates around them to close part of the magnetic circuit and reduce stray magnetic fields outside the package. The boxes are sealed, labeled with magnetic material warnings, and inspected one final time before shipment. From here, these small but powerful rare earth components begin their journey, becoming the magnetic hearts that drive electric vehicle motors, wind turbines, industrial robots, and electronic devices around the world. This concludes the journey used to create the most powerful permanent magnets on Earth. From rare earth ore buried deep underground, the material must pass through mining, crushing, flotation, chemical separation, metal electrolysis, Ndfeb alloy melting, rapid casting, powder milling, magnetic alignment, compacting, sintering, machining, protective coating, and finally magnetization using powerful electrical pulses. Hidden inside every small magnet is a manufacturing chain that demands extremely high precision. Even a minor error in alloy composition, particle size, crystal orientation, or sintering temperature can reduce magnetic strength, heat resistance, and service life. Factories must maintain extremely low oxygen levels, apply pressures of hundreds of megapascals, use temperatures reaching thousands of degrees, and rely on inspection systems capable of detecting extremely small defects. This process allows Ndfeb magnets to serve as core components in electric vehicle motors, wind turbines, industrial robots, medical equipment, hard drives, speakers, aircraft, and many advanced defense systems. They make motors smaller and lighter while still delivering high torque and efficiency. But this strength comes at a significant cost. Behind every magnet lies a vast volume of mined rock, complex chemical processing, high water and energy consumption, and the risk of waste sludge containing acids, heavy metals, or radioactive impurities. The supply chain is also concentrated in only a few countries, meaning that disruptions involving exports or transportation can slow factories around the world. A greater challenge will emerge as millions of electric vehicles, wind turbines, robots, and electronic devices reach the end of their service lives. If the magnets are shredded together with steel, plastic, and copper, neodymium, praseodymium, dysprosium, and terbium may be lost in complex waste streams. Yet old magnets do not have to end their lives in landfills. They can be dismantled, demagnetized, cleaned, crushed, or chemically processed to recover rare earth elements. In some technologies, the old material can even be recycled directly into new alloy powder, eliminating several steps required when starting again from mined ore. Can a magnet from a failed motor return inside a new electric vehicle? Can retired wind turbines become a raw material source for the next generation of clean energy? The answer lies in a different production line, where technological waste is transformed into a strategic resource. That is the journey of rare earth magnet recycling, which we will explore in the next video.